Hello, everyone, and thank you for joining us for today's e-showcase, Enhance Sustainability Through Improved Solids Management. We want to make sure that we send a huge thank you to today's sponsor, Kemira. And I have the honor and privilege of introducing today's speakers. Brett Offerman, Senior Account Manager with Kemira. Brett has over 45 years of drinking and wastewater industry experience, 26 of those years with Kemira, managing major water and wastewater accounts. He also has 18 years of experience operating various wastewater treatment plants and holds a California SWRCB Grade 5 Operator Certificate. Also with us is Richard Waterous, Senior Account Manager, Advanced Water Treatment, Kemira. Richard has 35 years of industry experience as well, and 18 of those years are Kemira. He has extensive experience with potable water and a wide range of wastewater treatment applications. And without further ado, I'm going to hand it over to our presenters.
Okay, can you hear me?
We certainly can.
Okay, let's get started with the first slide then. Next slide. Very good. Okay, go ahead, next slide.
Regina, it won't let me share. Okay, now it will. Sorry.
Okay, very good. Hey, everybody. So today, June 5th, is World Environment Day. So we wanted to raise awareness of how the water industry can make a positive sustainability impact through improved solids management. My colleague Richard Waterous and I will be presenting chemically enhanced primary treatment, or CEPT, and enhanced sludge dewatering and Struvite control. Thanks for joining us today. As Regina mentioned, Richard and I have extensive experience over the drinking water and wastewater industry, and we'll be presenting some cool stuff today. Go ahead, next. So today we're going to learn about chemically enhanced primary treatment, or CEPT, enhanced sludge dewatering and Struvite control, and the sustainability benefits of these techniques. Next. CEPT is a low-cost alternative to expensive and time-consuming capital upgrades required to expand plant throughput rates or remove bottlenecks. CEPT applications can be initiated rapidly, require minimal capital investment, and can be highly effective utilizing a plant's existing treatment process. CEPT involves the addition of iron coagulants, such as ferric chloride or ferric sulfate, and with or without the addition of polymers at the plant headworks, resulting in an increased removal of organic and particulate matter in the plant's primary clarifiers. Benefits of using iron coagulants, such as ferric chloride or ferric sulfate, include increased primary sludge bound for the digesters, increased TSS, BOD, and phosphorus removal in the primaries, which then reduces the load to the biological treatment, thus increasing aeration basin capacity and improving aeration basin performance, or alternatively reducing oxygen demand. By increasing plant throughput rates, this requires fewer primary clarifiers to achieve the same or higher rates of removal, which in return reduces energy costs in the aeration basin and dewatering costs, such as higher primary sludge content equals reduced dewatering polymer and higher cake solids. Iron addition in primaries will contribute to reduced H2S in the primaries and digester H2S levels, further contributing to improvements in biogas quality and volume. Iron salts are highly effective in removing TSS, BOD, and phosphorus. They also effectively remove dissolved sulfides in the waste stream, preventing the formation of H2S gas throughout the treatment process, including the digesters, for improved biogas quality. Primary clarifier removal rates achieved with iron addition are linear and can increase to as much as 90% TSS and BOD if desired. This table demonstrates the treatment efficiency of precipitation methods using iron coagulants. Direct precipitation is a primary treatment plant with no secondary treatment. Pre-precipitation is SEPT before the secondary treatment process. Simultaneous precipitation is the addition of iron salts into the aeration basin to assist with phosphorus removal in the biological system. And post-precipitation is the addition of iron aluminum salts after biological phosphorus removal to further reduce phosphorus with tertiary filters. This data is sourced from the Kemira's Water Handbook. CEPT significantly improves the reduction of organic matter in primary treatment. Phosphorus removal is also improved, and reduction levels can be controlled with the correct choice of coagulants and dosage. This figure shows the distribution of BOD removed in a wastewater treatment plant with and without CEPT from the Kemira Water Treatment Handbook. With CEPT, the distribution of organic matter changes, and the treatment efficiency of BOD and CEPT can be up to 75%, leaving just 15% of the BOD to be removed during biological treatment, as you can see in the figure in blue on the right-hand side. With CEPT, the activated sludge tank requires a much smaller volume, and therefore this footprint can be significantly reduced, as we'll see in a case study. The lower load on the biological treatment step results in lower energy consumption and less secondary sludge production. There is lower FM ratio and increased capacity in the aeration process. With CEPT, the hydraulic retention time can be reduced or the capacity of the wastewater treatment plant increased. The sludge production at the wastewater treatment plant changes with CEPT. More primary sludge is produced with CEPT and less secondary sludge. Since secondary sludge is normally more difficult to dewater, especially if it's anaerobically digested sludge, the solids content in sludge might increase by a few percent with CEPT. If there is no anaerobic digestion of the sludge, a CEPT process generates typically 10 to 15% more dry sludge. Primary sludge exhibits enhanced dewatering properties versus secondary sludge with lower sludge handling costs. Increased primary sludge equals increased biogas production, enhanced dewatering properties, and reduced dewatering cost. A plant can become more sustainable by increasing the amount of biogas produced during the anaerobic digestion of sludge. During conventional biological treatment, a large portion of the particulate organic matter is converted to carbon dioxide. Through CEPT, the particulate organic material remains intact in the sludge, which means it can be converted to methane gas in an anaerobic digester. This means that considerably more methane gas is generated when CEPT sludge is digested than is the case with secondary sludge. Biogas generation is, of course, highly beneficial since it can replace fossil fuels and reduce a plant's carbon footprint. It is clear that a CEPT plant has a higher biogas potential than those without CEPT. With a CEPT process, the energy needed to remove organic material can be dramatically reduced and biogas production increased. It is therefore possible to improve the energy balance of a wastewater treatment plant. In some cases, the wastewater treatment plant can be converted to an energy production plant. Iron coagulant injection point and mixing is essential for CEPT, and the polymer, along with the polymer addition injection point. With CEPT, the influent BOD is an energy source instead of an energy consumer. One point is crucial as well. There must be sufficient mixing time for the ferric iron coagulant before polymer addition. CEPT opens up a new source of bioenergy that can reduce the carbon footprint. Another advantage with CEPT is that it acts as a barrier before the biological treatment step. If the load is too high or there are some other disturbances in the biological process, CEPT reduces the severity of these disturbances. Since the load to a wastewater treatment plant varies throughout the day, with the load lowest during the night, of course, before a peak in the morning, high load during the day, and then a second peak in the evening. The peak is not only in flow, but also in concentration. This means that the load can change multiple times in a fairly short period. Since biological treatment works best when the load is constant as possible, CEPT can remove the worst peaks and smooth out the load. With the support of online control of the coagulant dose, it is possible to do this in a highly controlled way. Many municipal wastewater treatment plants face capacity constraints brought on by increased process flows derived from population growth, expansion of service areas, etc. Plant expansions can take years to materialize and cost tens of millions of dollars or more. Fluctuations in influent quality can adversely impact treatment efficiency, including the biological zone. CEPT is effective, proven alternative to costly plant expansion, yielding numerous benefits. Implementation of an effective CEPT program requires minimal capital investment. Let's go through some case studies. CEPT was developed in North America to counter the inability of plants to expand their treatment process due to lack of available space. There are a number of successful long-term CEPT applications in North America. Some examples of successful iron-based CEPT applications in North America include the following. This plant in Southern California was originally a primary treatment plant using CEPT successfully and then added secondary treatment designed around the CEPT application. They have upwards of 80% TSS and BOD removal. San Diego Point Loma is a primary treatment plant with no secondary aeration basins and has been using CEPT for over 30 years to remove TSS and BOD. The plant was averaging 90% TSS and 60% BOD up to 2021, but lately, due to changes system-wide with construction for pure water, the plant is at 86% TSS and 59% BOD. Miami-Dade North District conducted a long-term CEPT evaluation yielding the noted improvements. However, the project has been suspended due to capacity issues related to the underflow transfer pump's capacity, which is very important to note that when you have CEPT application, you will have more primary sludge, and you just need to make sure you have the pumping capacity to handle that. Okay, Richard, let's talk about enhanced sludge dewatering and Struvite control.
Thanks, Brett. Next slide, please. The microorganisms that make up the bulk of sludge surround themselves with a gelatinous layer that strongly attracts water. When sludge is dewatered, it must be processed or conditioned to break down this gelatinous layer. This releases the water so that it can be separated through chemical addition. The application of an iron coagulant to the dewatering process is known as enhanced dewatering. Ferric chloride or ferric sulfate are commonly used to enhance sludge dewatering. The problem? Enhanced dewatering can be used to overcome process issues such as struvite formation in deposits, poor machine throughput rates, high water content in dewatered solids, and poor centrate filtrate quality. The solution: enhanced dewatering conditions the sludge, boosting liquid-solid separation and thus enhancing the dewaterability in the solids handling process. The enhanced dewaterability results in higher cake solids, reduced dewatering polymer use, reduced hauling cost, increased machine throughput rates, and higher solids capture rates, which equal reduced centrate and filtrate TSS, ultimately resulting in reduced energy consumption and a smaller carbon footprint. There are platforms now available to the marketplace that can automate and optimize iron addition for this application. Six reasons why the use of iron for enhanced dewatering may be a good solution for your plant's operation. Number one, struvite elimination. Ferric chloride or ferric sulfate addition to eliminate struvite deposits results in reduced process downtime, maintenance, and equipment replacement costs. Reduced dewatering polymer dose. Iron use for enhanced dewatering reduces dewatering polymer demand as much as 55%. Drier cake solids. Reduced energy consumption and carbon footprint for the drying and transportation of sludge, improve machine throughput rates. Reduced phosphorus. Reduced phosphorus load returning to the plant's treatment process. Higher quality centrate filtrate water returned to the plant. Reduced phosphorus and solids loads equal improved treatment. And finally, increased dewatering capacity. Increased machine throughput rates can exceed 35%. The majority of enhanced dewatering applications begin with the plant's need to mitigate struvite formations and deposits. Struvite can be a big pain point for wastewater treatment plants. Struvite is a nuisance crystal that often forms in anaerobic digesters, sludge transfer lines, dewatering equipment, and centrate filtrate lines. Struvite forms when magnesium, ammonium, and phosphate ions are present under certain conditions. Struvite deposits can seriously limit machine performance and restrict sludge flows. Regular shutdowns to process operations may be necessary to pig, jet, or physically replace piping or other equipment due to struvite deposition. The addition of iron-based coagulants remove phosphate ions from the digested sludge and subsequently eliminates struvite formation. Iron use eliminates struvite depositions and prevents future struvite scaling. The photos on the left show typical weekly struvite deposits on the centrate line and centrifuge bowl for a large municipal wastewater treatment plant in the southeast. The after shots were taken after 4 months of iron use. Struvite elimination results in reduced process downtime, maintenance, and equipment replacement costs. Benefits of enhanced dewatering include drier cake solids. The use of iron coagulants for enhanced dewatering improves dewatered cake solids, typically from 3 to 5 percentage points. Reduced energy consumption and carbon footprint for drying and transportation of sludge. Improved machine throughput rates. Another benefit includes lower costs for transportation and sludge disposal. Higher dewatered solids percent TS and dewatered sludge equals fewer truckloads of sludge hauled. For cases where the biosolids are incinerated, higher cake solids equals increased energy recovery, higher BTU value. CO2 footprint reduction from sludge transport and energy savings from sludge incineration. Ferric addition for enhanced dewatering also reduces phosphorus levels in digested feed sludge. The concentration of phosphate ions can impact the dewaterability of sludge. Phosphorus precipitation through iron coagulant addition removes phosphate ions from digested sludge and reduces the phosphorus load returning to the treatment process from dewatered reject waters. Ferric addition for enhanced dewatering yields improved solids and phosphorus capture rates, resulting in higher quality centrate filtrate quality returned to the plant's treatment process. Reduced TSS and phosphorus levels returned to the treatment process contributes to improved treatment plant performance and reduced costs relating to the chemical usage if CEPT is utilized, as well as improved aeration operation. Next slide. Another benefit includes reduced dewatering polymer use. Iron use for enhanced dewatering reduces dewatering polymer demand as much as 55%. Benefits of enhanced dewatering also includes increased dewatering capacity. Increased machine throughput rates can exceed 35%. Enhanced solid-liquid separation increases water release rates that enable higher sludge loads to dewatering. Increased machine throughput rates can reduce the number of machines in use, reduce machine run times, and potentially manpower hours, extending machine life and contributing to further savings attributed to reduced machine maintenance and labor. The use of ferric iron addition in enhanced solids dewatering yields a number of sustainability benefits. These include the following: reduction in CO2 generation, tied to reduced machine runtime, reduced truckloads of dewatered solids, improved plant performance tied to improved centrate filtrate quality, increased dewatering capacity, energy savings, freight savings associated with reduced truckloads hauled for disposal, savings in sludge disposal costs. And finally, technology now exists to provide customers with 24/7 program transparency and KPI monitoring. Through Kemira's enhanced dewatering program, Miami-Dade South District's wastewater treatment facility was able to completely remove troublesome struvite. Miami-Dade South District wastewater treatment plant operates one of the largest wastewater treatment plants in the state of Florida, and it utilizes a high-rate activated sludge with pure oxygen treatment process, dewatering the plant's anaerobically digested sludge via 4 Sharples centrifuges. Wastewater flow at the plant averages a massive 100 million gallons daily, with sludge flow to the dewatering operation averaging 600 gallons per minute. The challenge at the plant. Struvite formation is a common challenge for wastewater treatment plants that utilize anaerobic sludge digestion. At the Miami-Dade plant, heavy struvite buildup had continued for years, and it was starting to cost them more time and money. Struvite impeded their dewatering operation and forced them to clean their systems on a weekly basis. This was time-consuming, resource-hungry, and caused unnecessary downtime. Worse, the struvite was also damaging their centrifuges, leading to frequent repairs and yet more downtime. Kemira was asked to solve the problem based on success with eliminating struvite at the Miami-Dade Central District wastewater treatment plant. Kemira's solution. Kemira's team recognized quickly that the amount of orthophosphorus in the sludge needed to be decreased. Utilizing wastewater treatment expertise, the right solution was identified through laboratory testing. The solution was based on Kemira's enhanced dewatering program using ferric sulfate addition. Kemira's solution can be customized to fit the customer's primary needs, such as struvite control or drier cake solids, or reducing dewatering costs per ton of sludge processed. The results. Only a week after being introduced, the results became clear when the plant system was open for a weekly washing. There was no struvite to be seen. In addition to struvite elimination, Miami-Dade is also reaping other benefits, including significant cost savings in man-hours needed for maintenance activities. Since its implementation, the solution has provided the plant with an extensive reduction in dewatering polymer demand, with the solids capture rates increasing from 87% to a whopping 99%. Cake solids also increased. And since this program has been implemented, Kemira has since continued working closely with the customer to provide solutions to other issues at the plant. Recapping, today's sustainability takeaways include the following. Chemically enhanced primary treatment, or CEPT, contributes to enhanced biogas production, reduced energy consumption, reduced dewatering costs, increased process capacity without capital investment. Enhanced dewatering contributes to CO2 reduction, increases in dewatering capacity, energy savings, savings in sludge disposal costs. We now welcome the opportunity to visit your facility to discuss one or more of our highly effective treatment solutions that enhance sustainability and optimize the treatment process. We now open the floor to Q&A.
All right. Thank you so much, Richard and Brett. That was great. I will invite everyone to go ahead and select the Everyone option in your chat module, and please provide us with some questions. We'll begin with our first question. What is better, ferric or porous? Is the first question.
Okay, yeah. So ferric chloride is the product of choice for CEPT, Fe+3, for a precipitating coagulant. The ferrous chloride will only go after the H2S, and you'd have to feed a whole lot more to precipitate solids. Right, Richard?
That's correct.
All right, perfect. Our next question is, ferric salts screw the percent volatile solids fraction, which negatively impacts the Van Cleek method. How does a plant with CEPT meet the vector attraction requirements for the 503 regulations?
Well, that's an interesting comment and question. And as you know, all plants have to do a 38% reduction of volatile solids. And I've never ran across a plant that has issues meeting the 503 regs. Richard, I don't know if you want to comment on that. I will have to look more up about the Van Cleek method, but I would be interested in getting more information from Carolyn on that.
I concur with you on that, Brett.
All right, perfect.
And I would ask her if she's seeing plants that aren't meeting the 38% volatile reduction with CEPT.
And so, Carolyn, if you can hear that, you may want to pop your response in the everyone option or the chat. And while we're waiting for that to come through, we do have one from Brad. Where would your addition or injection point be for the dewatering process?
I can answer that, Brad. It's upstream of the dewatering polymer injection point, typically in line. Kemira designs and fabricates a custom Schedule 80 PVC static mixer and injection ring to prevent any type of corrosion. We can also add the chemistry into a sludge holding tank if an inline application is not viable.
Okay. And Marcus asks, where would your addition or injection point be for Struvite control within an anaerobic digester?
Good question. We have direct digester applications as well as I noted previously, immediately downstream of the digester in the sludge feed sludge line leading to dewatering.
Okay, great. And I see that Carolyn did have a response. And so we're going to go ahead to Eric. Is this method good for removing specifically PFAS contaminated water? If so, how do you deal with the PFAS contaminated primary biosludges? And then we'll go to the one right before that.
Brad, I can't comment on that. Can you?
I'm sorry, which one is that?
Is this method good for removing specifically PFAS contaminated water? If so, how do you deal with the PFAS contaminated primary in biosludges? And then we'll go to the one right before that.
Yeah, no, we have yet to get into that. I know it's brand new in the wastewater industry for PFAS showing up in the sludge, but we haven't had any studies that, to my knowledge, showing if any PFAS is removed through CEPT. And and as far as your other question about how do you deal with it, yeah, that's a whole new ball game that's coming out.
All right, so we'll go to the one that was right before that. Any concerns about Vivianite precipitates in digested sludge and iron precipitation on UV?
As far as enhanced dewatering is concerned, the answer is no. As far as Vivianite, I've never personally experienced it. Iron precipitation on UV when you're dealing with enhanced dewatering, we obviously optimize the application to ensure that there is no free iron remaining. So the answer there is no. There's no detrimental impact on UV.
Okay. And Samuel asked, would the addition of ferric chloride be beneficial for a screw press process?
The answer is yes. The enhanced dewatering application utilizing iron applies to screw presses, centrifuges, and BFPs.
Okay. And Peter asked, could ferric be added to a digested sludge holding tank before dewatering in polymer injection?
The answer is yes. We do it presently. However, an inline injection point downstream of a digester or a sludge holding tank may provide more optimal results, but the answer is yes. We do currently add into digested sludge holding tanks.
All right, and again, we still have some time if anyone would like to post their question to the everyone option. And I am going to actually chat out Richard and Brett's contact information if you'd like to reach out to them after today's event. And so I see Brett has a correction. Carolyn meant to say, how can you sample before ferric addition?
Yeah, we're going to talk afterward. Very interesting.
Okay. All All right, I don't see any additional questions coming in. We do have some time for more questions if you do have them. Brett, Richard, is there anything that you'd like to add? We've got Eric. Does Kemira have any plan to initiate any study for CEPT to remove PFAS contaminated water and sludge, or to collaborate with some company to remove from the water and destruct the sludge?
Well, that's a great question. No, we don't have any plan at this point, but I'm glad you brought it up. We'll probably put it to our research and development group. They're the ones that would spearhead a project of this kind. But gosh, if you have any information on that you could pass to us, that would be fantastic.
I would like to add, Brett, that Kemira is a very research-intensive company. We're headquartered in Europe, and as Brett noted, we have R&D facilities around the world, both in Europe here and North America. It's definitely an up-and-coming subject, and if anybody is going to be spearheading any studies, it certainly would be Kemira.
Okay, we have another question that just came in. Can you add the ferrous to the common DWC centrate piping for Struvite control and removal?
Mark, it's a good question. First of all, it would be ferric chloride or ferric sulfate and not ferrous. It'd be Fe+3 for this application. You can add it to a centrate line. However, there are far greater economies of scale in conditioning the feed sludge itself. You're going to see a far greater economic impact on introducing it to the feed sludge versus the centrate line, including the improved machine throughput rates, including the increased cake solids, and including the reduction in dewatering polymer usage.
Okay. And Samuel has a question. Would injection before flock tank help with polymer and improve dewatering in a screw press?
The answer is yes.
Yes. And then he pops in and says ferric chloride injection.
Yes, and Samuel, we have the capability and the equipment to do very detailed on-site tests to identify optimal ferric dosage rates and to also identify the accompanying benefits and impacts on cake solids, dewatering, polymer demand, et cetera. So we basically go to each plant and customize the approach to fit each plant's needs.
And some great questions. You can keep them coming. We still have just a few moments. He says, I'll send both of you some of the information after this meeting. We have both PFAS removal and destruction technology in X Nano LLC. Okay.
Excellent.
Thank you, Eric. And so this one is comment from Kemira, Jennifer Hansen, Americans Commercial Team. We are following the developing PFAS regulations and exploring avenues for removal. Thank you for popping in, Jennifer. And there's a question in reference to, do you work in Canada?
Erica, as a matter of fact, we are the largest manufacturers of coagulants in Canada. We have plants around the country, but the answer is a quick yes. And in fact, I'm presenting this webinar today from one of our production facilities in Ontario.
Mm-hmm. Excellent. Okay, and let's see, Samuel has, we already dose ferric chloride to primary clarifier into our sludge line for anaerobic digestion. Would additional dosing specifically for dewatering be needed?
The answer there, Samuel, is with a site visit and laboratory tests, measuring ortho-P and other parameters through your process, we could make that quick determination. I will add that we already work with customers that have these same types of injection points and programs in place where, again, their feed sludge orthophosphorus levels are still quite excessive. So it all depends on visiting the plant and conducting measuring key parameters through your process to make that determination.
Yeah, for sure,
That's
Samuel. And
something
I guess I would question, are you having Struvite issues?
Okay, and as we're waiting for that response to come in, what would a typical dosage rate be prior to the dewatering centrifuges?
Brad, the answer there is it's typically between 2 and 3 gallons per 1,000 gallons of feed sludge flow.
Okay. All right. Any additional questions, Samuel, if you wanted to respond to Brett and Richard's comment to you? Right. I don't see any additional questions or comments coming through. And here we go, Samuel. We don't have any Struvite issue that we know, but haven't dug deep into dewatering. Thank you, Samuel.
Samuel, again, to your point, focusing on particular parameters throughout your dewatering process would be able to determine if there is indeed a problem or not.
Yeah, contact us. We'll have a chat.
He says, sounds good. Sounds good. Okay. All right. I don't see any additional questions or comments. Brett, Richard?
I'd just like to say, both Brett and I appreciate the opportunity to present to you folks today more information on these applications. Brett and I have extensive experience with both of these applications, and we welcome the opportunity to chat more in depth with you on an individual basis to determine where your challenges lie and what solutions we can offer.
For sure. And Eric, Richard, before we go, it looks like Erica had a question. We use ferric in the primaries and secondaries and still observe Struvite issues. Interesting. So it really depends on.
Yeah, we see that. Surprisingly, Erica, we see that quite often. If you want to reach out to me, I can certainly talk to you a little bit more in depth, but that's not an uncommon observance.
All right. And she says, thanks. And again, I've dropped Richard and Brett's email address in the chat. You can go ahead and copy that if you'd like to reach out to them after this presentation for additional questions or touch points. And Peter says he will be in touch.
Yeah.
All
Very
right.
good.
So this was
Appreciate
a great presentation. I want to thank Brett and Richard and definitely our sponsor, Kemira, for presenting today. This actually is going to conclude today's e-showcase. Thank you all for attending. The recording, again, will be available at wefbuyersguide.wef.org. We will send all registrants an email tomorrow with that link. And please visit our event calendar to sign up for a future webcast.
Yep. Thanks, everyone.
Thanks, everyone,
Thank
for your
you.
time. Have a great day.